If ever there was a mathematics topic obsessed with taking shortcuts to a process, then calculus might be it. Either when it comes to differentiation, where we're taught to learn the derivatives for many standard functions, rather than going through the full process of differentiation by first principles every single time. But perhaps less often focused upon is that the same is true when we're doing a proper integral too. And therefore, in today's Can We Do That video, we're asking the question, can we do integration by first principles? But because many of you have looked at the length of this video and probably deduced the answer to that is yes, I'm going to be more specific and say that we're going to be doing this by Riemann and Darboux sums to give their official names to the processes we're doing here today. But before we continue on any further, I must give you the usual warning, which is... yes, this video is covering things that you don't need to know for the A-level qualifications in England, and we're just studying this stuff for fun, because why not? Now, it's possible if you were to use the internet to do some research into the process of integration, you would come across all of these different approaches to that process. But as I don't want this video to last a lifetime, and also because I actually only came across half of these approaches when doing research for this video, I'm only going to focus on the Riemann integral and the Darboux integral in this video here today. Starting off by looking at the Riemann integral, we first need to have an understanding of what a Riemann sum is. But the interesting thing is, for those of you who have studied the Maths A-level qualification in England, you might secretly already know how to do these, or at least an example of one. That's because you might remember something called the trapezium rule, otherwise known as the trapezoidal rule in some other countries. This was the idea where we could start with the area enclosed by a function and then estimate the area by means of some trapeziums. Although we don't usually set out trapezium rule in a way that's consistent with how we should set out a Riemann sum officially, trapezium rule is technically a Riemann sum because it is trying to estimate the area enclosed by a function by splitting it into shapes in a vertical strip sort of arrangement. However, with Riemann sums, we're not just locked into having to use trapeziums. We could instead choose to use a shape that has an area that's easier to calculate, such as, for instance, a rectangle. And unsurprisingly, if you were to try to estimate the area in this way, it's called the rectangle rule. Yeah, kinda makes sense really. Interestingly, there is more than one approach to the rectangle rule though. You could have the rectangles arranged so that the top left-hand corner of each rectangle is intersecting with the curve, as you can see demonstrated on the screen right now. Or alternatively, you could have it so the top right-hand corner of each rectangle is intersecting with the curve. Or even so that the middle of the top of each rectangle is intersecting with the curve. In each case, the y-coordinates in those positions are then deciding the height of each rectangle. And to continue on the path of giving all these things nice logical names, these processes are called a left Riemann sum, a right Riemann sum, and a middle Riemann sum respectively. The accuracy of your estimate is affected by how concave your function is when you're looking at a middle Riemann sum. Whereas when you're looking at an increasing function, a left Riemann sum will provide an underestimate and a right Riemann sum will provide an overestimate. And then this is all flipped on its head when it comes to looking at a decreasing function. But if a Riemann sum is just an estimate for the area, how can we then find the actual area, what's known as the Riemann integral? Well, if I was to try to explain this in the most straightforward way, I'd say that we've just got to take the number of rectangles fitted into the space, let's say n, and make n tend towards infinity. Or alternatively, instead of having n as the variable of note, we could express the calculation in terms of h, where h is the width of each rectangle, and therefore what we'd end up doing is making the width of each rectangle tend towards 0. And so now that we've had a look at what a Riemann integral is trying to do, let's take a look at an example. We're going to calculate the Riemann integral of the function 5x between 0 and 4, using specifically a right Riemann sum for our approach. And to begin with, it's often helpful to try and visualize what it is you're trying to calculate. So I've drawn a graph of the function in question, although that does technically mean we are just trying to work out the area of a triangle, but that's just because I tried to keep this first example nice and simple, so we're not actually going to use the standard formula we already know for calculating the area of a triangle. And instead, we're going to split this area up into n rectangles. But if we're trying to fit n rectangles in the interval from 0 to 4, that means the width of each of those rectangles individually would be 4 over n. And then, as we're doing a right Riemann sum, I'm going to draw the rectangles on so that the top right-hand corner of each rectangle is intersecting with the function. But that therefore means if we want to calculate the height of each rectangle, it's going to be decided by the coordinates of that specific corner for each specific rectangle. The right-hand side of that first rectangle is one rectangle's width away from the point x equals 0, therefore meaning it's at 4 over n. And then the second rectangle's right-hand side is at 2 lots of 4 over n, 3 lots of 4 over n, so on and so forth, all the way until we get to the last rectangle whose right-hand side is at 4. Therefore, we can find the r term rule for this sequence, which would be 4 over n lots of r, running from r equals 1 all the way to n, which conveniently means if you were to plug n into this formula, you would end up with just what we want, which is that the nth rectangle is at x equals 4. But if the x values are following a sequence and the y values are given by the equation y equals 5 of x, the y values are also following a sequence, because we can take that r term rule and plug it into that function to get this, which then simplifies to 20 over n lots of r. But therefore, if the y coordinates of these points are deciding the height of each of these rectangles, all we've got to do to work out the area of the rectangles is multiply these y values by the width of each rectangle, which we already said was 4 over n. Therefore meaning the total area of all our rectangles is the sum of all the rectangles in this sequence from r equals 1 to n. This is the Riemann sum for our integral. But although we could then go ahead and multiply out the brackets to get 80 over n squared lots of r, we could also choose to turn this into a Riemann integral by just doing the limit as n tends towards infinity of this Riemann sum. So let's go ahead and do this calculation to work out the area of the integral. So starting off by realizing that although we've got that 80 over n squared there and the n is the variable for the limit, for the purposes of the sigma notation, it's the r that's the variable. So the 80 over n squared is going to effectively be treated like a coefficient in front of that r. So all we've got to do is work out the sum of r between r equals 1 to n, which is of course a formula of half n plus 1. You could of course then multiply out the brackets, but then you're probably going to want to split up that fraction into these two separate terms, because then interestingly, now we can calculate the limit. Because as n tends towards infinity, as the only place where the n is now appearing is on the denominator of a fraction, that means that fraction will tend towards 0 as n approaches infinity. Therefore meaning this comes to 40. And there we go, we've done it. That's what this integral comes to, which is precisely what you get if you just worked it out as the area of a triangle. Therefore meaning this calculation does make sense with what we would expect. But okay, that was the area of a triangle, which wasn't particularly interesting, so let's now try and do the Riemann integral of something a little more spicy. We're going to work out the Riemann integral of 6x squared plus 7 over the interval 1 to 3, using this time a left Riemann sum. That means the diagram will be slightly different, and it also affects the sequence of x values that we're choosing for our rectangles. So let's take a look, starting off by drawing a diagram, and again we're paying attention to which type of Riemann sum we're doing. So therefore the top left hand corner of each rectangle in this case is intersecting the function because we're doing a left Riemann sum. And because we're fitting n rectangles between 1 and 3, that means the width of each rectangle can be calculated by finding the space in between the numbers 1 and 3, which is 2, and sharing it equally between those n rectangles, which comes to 2 over n. So that means we can now focus on how we're going to calculate the height of each rectangle by realizing these coordinates will decide the heights. And therefore we need to know the x coordinates. The first x coordinate is of course going to be 1, but then the second x coordinate is going to be a gap of 1 rectangle's width away from 1. So that would be 1 plus 2n, and continuing that on, we're again going to get a sequence. And because once again these values are just forming a nice arithmetic sequence, it doesn't take that much effort to find the r term for this sequence of x values as well, which comes to 1 plus 2 over n lots of r minus 1, or alternatively 2 over n lots of r plus 1 minus 2 over n if you multiply out the brackets. We can then plug those x values into the function to get the sequence of the y values, which will ultimately decide the height of all the rectangles in our Riemann sum. But before we continue on any further, let's do some algebra rewriting with this stuff. We could first multiply out the brackets to get something like this, and then with some further tidying up and multiplying out of the brackets, we'll get this, and then multiplying those big brackets by 6, and then combining like terms and adding that 7 on, will eventually lead to this. All we then need to do to work out the Riemann integral is to work out the limit as n tends towards infinity of our y-coordinates, which was the height of the rectangles, times by the width of each rectangle, which we previously established to be 2 over n. And yes, we are going to go ahead and evaluate this, because I'm sometimes told by students that they hate it when in class we just go through one of the easy examples, which then feels completely different to the more involved examples they have to go through in their own time. So you know what? Let's do an involved example here today, although it is going to take a significant amount of algebra. So first of all, multiply out the big brackets to get this, and then realizing we can apply the sigma notation individually to the r squared, r and 1, because the r is the variable for the sigma notation, and the n is going to be treated like a constant until we come to evaluate the limit part of the notation. So therefore we can now apply the individual series formulas for those things, which will lead to this. That's then going to take a hell of a lot of algebra rewriting and combinations of fractions, and then even more rewriting and multiplying out brackets to get this. And although at this stage you could evaluate the limit, just to make it a bit easier for me to explain, I'm also going to gather like terms at this stage to lead to this. And then, what do you know? Once again, as we make n tend towards infinity, we only have n appearing on the denominators of fractions, which means those fractions will tend towards 0 as n approaches infinity, meaning we're just left with that 66, the constant term, and that is indeed the value you would get if you were to approach this integral in the usual quicker way. And that's really interesting to me, because it means we actually are calculating the area of these more awkward curved functions and being able to give a definitive value to them. But some of you might not still be convinced. Because we're doing a left Riemann sum applied to an increasing function, the area of the rectangles was always providing an underestimate. So although we are still applying this limit to make the gap get smaller and smaller and smaller, how do we know that there isn't still some kind of difference between the number we've calculated and the actual area under the curve? In other words, is something Riemann integrable or not? Well, if you look up the official definition of that, you will come across this, which both looks horrible, but is also pretty inconvenient to work with when trying to decide if something's Riemann integrable or not. There's potentially quite a lot of notation and terminology to unpack here in this definition, and therefore, as I'm trying to keep this video more focused on the calculations rather than official definitions, we're going to leave that for now. No fear though, because if you're interested in more fully understanding some of this notation, as well as more of the official definitions of the content coming up in the remainder of this video, I will be covering that in my next video as part of my spin-off Can We Do That Some More series. So therefore, what is an alternative way of deciding if something's integrable or not? Well, it's by looking at something known as the Darboux integral, which is what we're going to focus on now. The Darboux integral works by trying to place bounds upon the area enclosed by the function. First of all, by providing an upper bound by using the area of some rectangles that overestimate the area. We call this the upper Darboux sum. And then also we try to place a lower bound on the area of the function by using some rectangles that underestimate the area of the function. We call that the lower Darboux sum. And then, although the official definition is more nuanced than this, again it's something we're going to cover and talk about in more detail in the follow-on video from today, we can then apply limits to convert these two things into the lower Darboux integral and upper Darboux integral. Then once that process has gone ahead and happened, by squeeze theorem, if the lower Darboux integral is equal to the upper Darboux integral, then it means that the actual area of the function has been trapped between those two things at a specific value, therefore telling us that the function over the given interval is Darboux integrable. But then how do we actually carry out some of these calculations? How do we find a lower Darboux sum or an upper Darboux sum in the first place? Well, focusing on the lower Darboux sum first of all, it can ultimately just be calculated using rectangles once again. All you've got to do for the lower Darboux sum is ensure the height of each rectangle is chosen in a way so it means the y value that calculates it matches the lowest y value for the respective subinterval of that function. Again, the definition is technically a bit more nuanced than this. I'm trying to explain it in the simplest way possible, but just so I'm at least signposting towards some of the actual correct terminology for this stuff, the y values are the infimums for each respective subinterval for the function. But just in case I've lost any of you, as a reminder, I said the lower Darboux sum has to be providing an underestimate for the area enclosed by the function, and therefore the rectangles we're going to use to calculate it have to be fully below the function itself. So that could look like this, and therefore that does mean, actually interestingly, if you have an increasing function, then a left Riemann sum would act as a lower Darboux sum. Or alternatively, if you have a decreasing function, then a right Riemann sum would act as a lower Darboux sum alternatively. And so therefore you do have to be careful. If you've got a function that's got both increasing and then separate decreasing parts, then that's going to change whether you're using left Riemann sums or right Riemann sums for those individual parts. And also, as I said, it depends on what type of curve you have as to what type of Riemann sum you need for specifically the lower Darboux sum. And then conversely, the upper Darboux sum can just be calculated once again using rectangles, but this time the rectangles are calculated in a way so the y value is matching the greatest y value of the function for each respective subinterval. And once again, at least signposting some of the correct terminology, the y values for each rectangle are acting as the supremum for their respective subinterval. But again, in terms of calculations, that can be done actually by a Riemann sum. You'd be using a right Riemann sum if you've got an increasing function and a left Riemann sum if you've got a decreasing function. Okay, let's put this into practice by calculating the Darboux integral of 6x squared plus 7 between 1 and 3. So let's start off by calculating the lower Darboux sum for this integral. But the good news is, if we're going to draw the rectangles so they are fully below our particular curve, we realise that therefore the top left-hand corner of each rectangle is touching the curve, which means it could be done by a left Riemann sum, which we already did in the previous example. So the left Riemann sum we did before can act as the lower Darboux sum, and therefore we can turn that into a lower Darboux integral by taking the limit as n tends towards infinity to once again get 66. Once again acknowledging that we'll go into more detail about the official process that takes us from a lower Darboux sum to a lower Darboux integral, but also pointing out that the process we are doing here is perfectly valid for the types of examples that we're doing in this video. But what about the upper Darboux sum? That's going to be calculated by placing the rectangles in the way that you can see right here, so that the area of the rectangles is definitely above the area enclosed by the curve. And therefore, because the top right hand corner of each rectangle is intersecting the function, we can calculate the upper Darboux sum by just doing a right Riemann sum. And so therefore, good news is, we already know how to do this process. So we could then work out the r term for the sequence of x values that provides the right hand side for each of those rectangles. Take those x values, plug them into the function to get the r term for the y values, which is ultimately going to be deciding the height of the rectangles. And then we could work out the upper Darboux sum by ultimately taking those y values, the heights, and multiplying them by the width of each rectangle, which is 2 over n, as calculated in the second example we did. Of course, then we just have to do a load of algebra to then calculate what this is going to be. So of course we could multiply the brackets even more and gather like terms, multiply even more brackets, and then we're in a position when we can start to apply some series formula. The series formula for the constant term, the sigma of r and sigma of r squared, are as follows, as you can see on the screen right now, quoting those classic formulas. Then doing some more algebra simplification, and even more will lead to this, meaning we can then collect like terms, which will get us this. And that is going to be our upper Darboux sum. To then be able to convert that into the upper Darboux integral, we've just got to do the limit as n tends towards infinity for this upper Darboux sum. And therefore, once again, we've got fractions with n's on the bottom, so those are all going to tend towards 0, meaning we're just left with 66, which, what do you know, is the same as what we got for the lower Darboux integral, which means that the area enclosed by the function must be greater or equal to 66, while also simultaneously being less than or equal to 66, which by squeeze theorem tells us the area is 66. And therefore that really does confirm it. The function over the interval 1 to 3 is definitely Darboux integrable, and the area is definitely 66, even though we had a curve and we were trying to estimate the area using rectangles, because the smallest overestimate and the biggest underestimate both ended up being the same value, meaning the actual value had to be that as well. But some of you might be wondering, how does this relate to the usual process we do for integration? How do antiderivatives help us find area? Well, there is a more general proof to this that I will be going through at some point in my Prove It series, but for the moment we can look on a case-by-case basis about how adding 1 to the power and then dividing by the new power when doing polynomial integration can help us find the area enclosed by the curve. To help demonstrate this, all we've got to do is realise that the indefinite integral of x cubed with respect to x is actually very similar to the integral of t cubed with respect to t over the interval from 0 to x. Those two things come to the same thing, except for the fact you have to get rid of the integration constant that would be applied as part of the indefinite integral. Both of them would in that case come to x to the power 4 divided by 4. So therefore, all we've got to do is do the integral of t cubed with respect to t over the interval from 0 to x to show this in action. I'm going to do this using a Riemann integral with a right Riemann sum. Once again, we can draw our rectangles. We can realize we're fitting n rectangles between 0 and x, meaning each rectangle has a width of x over n, meaning we can then work out the sequence for the x values using the same process we've been doing several times in this video, and then the sequence for those x values can then be plugged into the function to give the sequence for the y values. But then all we have to do is work out the Riemann sum by multiplying that by the width of each rectangle, meaning we end up with this integral being equal to the limit as n tends towards infinity of the sum from r equals 1 to n of x over n times by x over n lots of r all cubed. Oh, blimey, that was a mouthful to say. And so therefore we're going to go ahead and evaluate that. Of course, multiplying out the brackets will get us this, and then the n and x are going to be treated as constants for the sigma notation, meaning we can apply the series formula for r cubed, which gets us this. Some more multiplying out of the brackets will then lead to this, and then we can split up that fraction into individual terms, meaning we'll end up with this. And then making n tend towards infinity, that's going to once again cause all the fractions with an n on the denominator to tend towards 0. Meaning in those most inner brackets, we're going to be left with just 1. So therefore, we've got one lot of 1/4 x to the power 4, which is 1/4 x to the power 4. Amazing! You can see right here in action how adding 1 to the power, then dividing by the power, helps us calculate the area under the curve. Cool. But ultimately, we've only scratched the surface. This video might lead to further questions such as how do we calculate Riemann integrals of functions such as this or this. But even more interestingly, you might be wondering, even if we keep it simple and stick to polynomials, what happens if we want to work out the integral of something like x to the power 4? Surely that means we'd need the series formula for r to the power 4, which would be the case. But if you're a further maths A-level student in England, you're only aware of series formula for r to the power of 0, r to the power of 1, r squared, and r to the power of 3. So that begs the question, do series formula exist for the higher powers of r as well? But this video has been long enough, So that is interestingly what we're going to be focusing on in the next video in the Can We Do That series. So stay tuned for that. Please remember to subscribe to the channel, like the video, and turn notifications on if you want to stay up to date with all my future videos. These videos take so much effort to create, so I really do appreciate the support. And with all that said, thank you for watching this video to the end. On the screen will appear a link to another video in my Can We Do That series if you're interested in exploring maths some more. And also in 3 days' time, a link to the follow-on video to this in the Can We Do That Some More series will also be appearing. So do check that out. Thank you and goodbye.